Welcome to the section on Laplace transforms. Today we're going to talk about finding Laplace transforms with the definition and then with the table. Just like derivatives, Laplace transforms have a definition. It's difficult to find a Laplace transform using the definition, and so then we have a bunch of shortcuts, and those shortcuts are encoded in the table. And then we'll end with what functions have Laplace transforms. So first, let's motivate why we're doing this. Laplace transforms are really good at helping us solve differential equations where the driving function g of t is discontinuous. And in real life, that can happen quite a bit. Here are two examples. I'm not going to read through them all, but I'll just briefly outline what's going on. In our mixing example, we've got an AB valve, and when valve A is open, we've got brine of a certain concentration going in, but then that valve closes, and when valve B is open, we have brine of a different concentration going in. So that's going to cause a sudden jump in our rate in. That's a discontinuous function. All right, and in an RC circuit, using Kirchhoff's law here, suppose the electromotive force E is an on-off switch. So again, that's going to be discontinuous. It's going to be off and then on and then off again. And that's going to create a piecewise defined function for your driving function. We'll be able to solve these differential equations using Laplace transforms. And so here's an image of how it works. And for my image, I've used the mixing example. Okay, so we start with an initial value problem that involves little x and t. So our goal is to solve for little x of t. We want to solve that initial value problem. What we do is we send that through the Laplace machine. And what happens is little x gets transformed to big X, and the variable t gets transformed to the variable s. So now, instead of little x of t, I have big X of s. And what I do is I solve this equation for big X. So this equation will involve, as you can see here, it involves s's and big X's. We solve for big X. That's over here. Then we run that through the inverse Laplace machine to come up with our final answer. That's got a sad face because typically that requires a bit of work, a lot of partial fractions. All right, and so now big X of s gets transformed to little x of t, and we've got our solution. Okay, let's look at the definition of the Laplace transform. Typically, we're going to be looking at a function, little f, defined on t greater than 0. We take the Laplace transform of this function by integrating from 0 to infinity the function multiplied by e to the negative st dt. And the notation is when we take the Laplace transform of a lowercase variable, we change it to an uppercase variable. And sometimes we'll just do that shorthand. L of little f is big F. And it's understood big F is a function of s, whereas little f is a function of t. And the one we'll use the most often is little y and big Y, because typically our differential equations will be given in terms of little y. Before we use the definition to find some Laplace transforms, I just want to mention that in terms of our image here, we're only today working on finding Laplace transforms. So we aren't even up to this first step yet. We're simply finding the Laplace transform of some functions, but we don't know yet how to take the Laplace transform of a differential equation. So we're going in baby steps. Okay, this first one, we want the Laplace transform of the function 1. So that's script L of 1. Now, when we use our table, let me show you how the table works. I digress. So here's your Laplace transform table. You should probably print this out and use it for the whole chapter because it will be your Bible and it will give it to you on tests. And the way you read it is the functions are in the left column and their Laplace transforms are in the right. So L of 1 should be 1 over s. That should be our answer. Let's see if that happens. Okay, so L of 1. By definition, that's what a triangle over an equal sign means. By definition, we want to integrate from 0 to infinity e to the negative st times 1. Now, that's an improper integral. And in past classes, what we would do is rewrite that as the limit as k goes to infinity of the integral from 0 to k. But I think we've all reached a level of mathematical maturity by this point, so we can leave infinity as our upper limit and just understand that it means we're taking the limit as k goes to infinity. All right, so here we go. I've started us out. I integrated. Now remember, the variable of integration is t, not s. So my integral is negative 1 over s e to the negative st. So this is negative 1 over s, which is constant. I'm going to pull that out, and I get e to the negative s times infinity minus 1. E to the 0 is 1. Okay, now there's a certain condition I'm going to need for this integral to exist. In order for this term to drop out and not be infinity, I'm going to need s is positive. So I'll just make that requirement. We're allowed to put any restrictions we want on s in order for our integral to converge. So up here in the definition box, the domain of big F is the set of s for which the integral converges. Now, in this first section, your homework's going to be a little bit concerned with restrictions on s, but pretty soon we'll just drop that and we won't even worry about it. So this is just 1 over s, which is indeed is what we thought we should get. Okay, let's do a couple more before we move on and use our table. This next one, the Laplace transform of e to the 2t, we'll see from our table that L of e to the 2t should be 1 over s minus 2 as long as s is bigger than 2. But let's verify that using the definition. All right, and again, I've started us out. I've written down the integral that determines the Laplace transform. And then in order to integrate, what I did was I combined these two terms as e to the 2 minus s all times t. All right, now I'm going to integrate 1 over 2 minus s e to the 2 minus s t straight bar 0 to infinity. Now 1 over 2 minus s is a constant. I'm going to pull that out. And then I have e to the 2 minus s times infinity minus e to the 0, which is 1. Now, in order for this term to drop out and not be infinity, I need s to be larger than 2. So if s is bigger than 2, then I'm going to get negative 1 over 2 minus s. And indeed, that is 1 over s minus 2. Okay, last one is a piecewise defined function, so you're not going to see a formula for this in your table. You have to do this using the definition. So the first thing I need to do for this function over here on the right is write down a piecewise defined equation for that. So f of t is, well, that's 2t. I can see that line as slope 2 if t is between 0 and 1. And then it's 0 if t is bigger than 1. Now, the Laplace transform is defined in terms of integrals, so whether you put greater than or equal to 0 here, or strictly greater than 0, it will not affect the Laplace transform. I'm going to leave it as greater than. Now, the integral from 0 to infinity can be written as the integral from 0 to 1 plus the integral from 1 to infinity. And the reason why I want to break it up is because 1 is the point at which the function actually changes. So if I integrate from 0 to 1, my f of t is e to the 2t. So that'll be my first integral. And my second integral goes from 1 to infinity, but fortunately my f is now 0. So this whole second integral just drops out. And I'm left with just the first integral, which is not improper at all. And you are going to integrate that using integration by parts. And I went through the steps, and I'm not going to read through them. You can read through them on your own and make sure you verify those steps. All right, let's practice using the table. The only thing you need to know in order to use the table is that the Laplace transform is linear, and that means constants can come out of Laplace transforms, and Laplace transforms distribute over sums and differences of functions. There are two examples right there. So this first one, you're going to do this part in your head. L of sine 2t plus L of t squared. That's a mental step. Typically, you're just going to jump right to the answer. Now, this first one is formula 6 with b equal to 2, and the second is formula 2 with n equal to. So if I just read off the table, I get 2 over s squared plus 4 plus 2 over t cubed. Okay, next one. Again, that 2 there is a constant. Mentally, I'll just pull it out and find L of e to the negative 6t using formula 3 in my table with a equal to negative 6. So if I take L of e to the negative 6t, I'm going to get 1 over s plus 6. I multiply by 2 to get 2 over s plus 6. So if I went too fast for you, what I did there is I wrote that as 2L of e to the negative 6t, and then I used my table on e to the negative 6t, and then I multiplied my answer by 2. Okay, next one, that's formula 5 with n equal 5 and a equal negative 1. And so that's 5 factorial, which is 120, over s plus 1 to the 6th. Okay, next one, it looks closest to formula 9, and my a is 4, and my b is 3. So that's s minus 4 over, so this is equal, s minus 4 squared plus 9. Okay, next one's a combo. L of 5, think of that as 5 times L of 1. L of 1 is 1 over s. So this will be 5 over s minus, the next one's going to be 1 over s minus 2. Now, in some of your homework problems, they'll ask you, I believe, in this section, for what s these formulas are valid. Well, this first guy is valid on s greater than 0. The second guy is valid on s greater than 2. You're going to pick the more restrictive of the two. If you want these formulas both to be valid, then you're going to have to say s is bigger than 2. Okay, finally, what functions have Laplace transforms? Well, in a nutshell, they can't grow too fast and they have to be piecewise continuous. So can't grow too fast, that means they have exponential order. It means they don't grow faster than m e to the ct, where c is a positive number. That's because in the definition of Laplace transform, you want to get an integral that converges after you've multiplied by e to the negative st. Piecewise continuous means you can only have jump and removable discontinuities. Here's the definition right here. No asymptotes. And here's a more thorough definition of exponential order if you're interested. And then in the interest of time, I've already graphed this last function here. And the question is it piecewise continuous? Yes, it is. No asymptotes, just one jump discontinuity. And that is the end of this section.